Bem, agradecemos ao Jorge e seguimos com a apresentação do professor Vladimir Mironov, como imprimir órgãos. Ele vai apresentar os conceitos, desafios, evolução e tendência da tecnologia da biofabricação de órgãos humanos, partindo da teoria da capacidade natural do organismo em se auto-estruturar para formar novos tecidos. Professor Vladimir Mironov, pesquisador e diretor do Centro Avançado para a Biofabricação de Tecidos da Universidade Médica da Carolina do Sul, dos Estados Unidos, inovador nos conceitos da bioimpressão de órgãos, possui as publicações mais referenciadas na área globalmente. O professor Vladimir Mironov tem estado conosco por um período de 3 meses na nossa divisão. Passo a palavra para ele.
Bom dia. It's a great pleasure to be on this symposium. At first, thank you very much for invitation. It's my third visit to this place, and it became addictive. And this time it's a long visit, so it's not just talking, but also collaboration. And you can see some result of our collaboration already, and I will show something also. So, what I tried to say today is basically 2 things. I believe that you can print human organ, and second, you couldn't print this without collaboration with STI. So that's the explanation why I'm here. Now, let me say that there's already some tissue engineering product on the market. For example, Cytograft developing blood vessels, completely biological, no any polymer, no any scaffold. It's only one problem, it takes 9 months to create these blood vessels. So we take biopsy, create monolayer, roll this, incubate 2 months, then kill all cells, create some kind of scaffold, but cell-derived, natural derived, and also patient-specific derived cells, scaffold. Then you again roll monolayer of fibroblast, and again incubate in bioreactor, and finally put this endothelial cells. So whole cycle is 9 months, and the cost probably $35,000. So it's not very cheap. Now, Anthony Atala, already 15 years ago, take scaffold, synthetic and natural, put this in bioreactor and create bladder. And there's already some patients already 15 years using this tissue engineering organ. So tissue engineering organ is a reality. But if you make sections, it's basically very, very flat organ. So we're focusing our efforts on building vascular tree, because without vascular tree, you couldn't create thick organs. Now, I believe that if you want to create organ on industrial scale, you must use automated robotic approach, which is basically rapid prototyping. And rapid prototyping, or now it's called additive manufacturing, it's already well-established field. First patent was in 1985, first company next year. Now it's already $1 billion business. Application of rapid prototyping in tissue engineering a little bit later, probably 10 years late. And of course, people at first tried to use existing machine and existing polymers and tried to build scaffold. So it's not surprised that on top papers in this field, 9 of the papers talking about scaffold. So basically, scaffold is biodegradable, temporal, chemical polymer which can be removed. And only our paper from the beginning started to talk about tissue-based approach. We still use some scaffold, but not solid, we use hydrogel. So this is our definition of organ printing. When I was in San Francisco, I saw this starter, and I say, wow, this is exactly what we try to do. So basically, again, this is definitely robotic computer-aided. But the key element is the layer by layer additive biofabrication. So basically, it's bottom-up approach. When you use scaffold, it's already top-down approach. And the problem is, when you have a layer, you have freedom to put cells when you want. When you have three-dimensional scaffold, it's very difficult to put inside in precise condition if there is, for example, 20 different cell types. Now, the market is, of course, huge because in the United States, it's not allowed driving bike without helmet, so the number of donors reduced dramatically and demand still huge. So you see the gap increases. It's called classical unmet need. So people dying and waiting until they get kidney, for example, and cost of dialysis $75K during 10 years, it's already $1 million. So it's huge cost for healthcare. And the idea is if we can create organ from human cells using human images and this bioprinter, number one, we can save life. Number two, we can reduce cost for healthcare at least twice. And number three, we can create profitable bioprinting industry. So this is a classical win-win situation. Now, this is the slide to which, again, it's used from classical rapid prototyping, but adapted to tissue engineering and bioprinting. You can divide all process on 3 steps: pre-processing, processing, post-processing. You start from clinical imaging, use computer-aided software, and create blueprint. And I will try to explain you that clinical imaging and blueprint is not the same things, because you're dealing with living tissue. And of course, according to my training, I am MD and PhD in development biology, so I'm not expert in this field. That's why I came to the place where you have real expertise in software and computer science. Now, the real process of printing you can compare with book printing. So, if I want to print book, what I must have? I must have text, paper, ink, printing press, and movable type. Now, if you want to print organ, I must have computer-aided design or blueprint. I must have bio-ink or self-assembling tissue spheroid. I must have bio-paper or bioprocessable, biocompatible hydrogel. I must have bioprinter, and I must have nozzle, which can allow to dispense them. But when we finish printing, it's not real organ, it's just, we call this tissue construct. And in order to move from tissue construct to real organ, you must use this another device, which is called bioreactor. So you must use special factors which stimulate tissue maturation. You must monitor this without disruption to non-destructive, non-invasive monitoring. And finally, you must have this bioreactor. Now, this is our scheme which we published in 2003. Now it's most cited paper in this field. We decided to focus on, at first, this is Lego game, you know, what you can do from tissue spheroids. We imagine all possible geometry, and finally decide that probably blood vessels most important. We divide blood vessels on 3 segments, large diameter, intermediate, and small. And I think we are close to finish this, and then next step is actually really printing organ. Now, let me say something about tissue spheroids. Tissue spheroids is basically a group of living cells which stick together. Cell aggregates, tissue spheroids. Some people now call this microtissue. So if you cut embryonic tissue and put this in a petri dish, they will, in hanging drop, they will round it. If you put 2 pieces of tissue close to each other, they will fuse. If the tissue have different mechanical property or cohesion, then you have enveloping phenomena. And if you have mixture of cells with different level of cell adhesion receptors, then you have cell sorting process. And if you put these tissue spheroids on plastic, they also spread like fluid. So if you look on these pictures, you can say, yes, tissue look like fluid. Then why could it flow? The difference is that there is also cytoskeleton inside of the cell. So you could not say that tissue is a viscoelastic fluid. So I talk with physicists, with biophysicists, and say, look guys, if it's behave like fluid, it look like fluid, why it's not fluid? They say, because it's not fluid. It's soft matter. What is soft matter? I don't know. But the point is it can fuse. That's most important for printing technology. So our assumption was that if we have tissue spheroids, and if we can put them close to each other, according to specific geometrical pattern, they can fuse. And in our PNAS paper, we proved this at first mathematically and then practically. Of course, it can be negative outcome, like this and this, and you can see it here. But if you find right hydrogel and right cells, then you can get this fusion. Another interesting thing is that if you look on diameter here and here, you can see retractions. That's why we couldn't use directly imaging which you can get from patients. So we must modify clinical imaging in order to get model. So it's again demonstrate that if you take tissue spheroids, put them, they start to fuse and diameter reduce dramatically. So you couldn't just follow the standard clinical imaging without developing blueprint. Another interesting characteristic, if you labeled cells which form aggregate and put them together, you can see there is no any cell migration, there is no any mixing. So tissue fusion is fusion without cell migration, without mixing. That's another interesting phenomenon of this process. Now, this is the first blood vessels printed robotically with Gabor Fogach. He used our printer. And you can see the tissue spheroids, you can see lumen. So robotic printing is a reality. Now, we have also luminized tissue spheroid when you have nothing inside. And if you put this luminized tissue spheroid, green cells is endothelial cells, which prevent thrombosis, and red cells is smooth muscle cells. If you put together, you have one. So basically, the idea is you have a lot of these spheroids, you can create branching tree. And this is the idea using nanoparticles. If you create Janus-like structures and then induce lumen formation, then these aggregates can find each other. That will be not directed tissue self-assembly, it will be self-directed self-assembly. And there is already 3 papers about using tissue spheroids with nanoparticles, magnetic nanoparticles. So if you put these spheroids in collagen hydrogel, you can see they fuse and you can create branching structure. So what I try to say that, yes, vascular tree is very complex structure, but if you use solid spheroids, you can build a tube with large diameter. If you use luminized or uniluminal tissue spheroids, you can build intermediate structure. And if you build several segments with this and several segments with this, practically you can build 2/3 of vascular tree or even more. So we don't want to build vascular tree per se. We want to build vascular tree inside of tissue construct. So yes, we're focusing at first on this system, but eventually we want to create solid organ without any empty space. So we use solid tissue spheroids, green is smooth muscle cells, red is endothelial cells, and if you put them like this, they will fuse and the endothelial cells sorted out inside. If you have luminized tissue spheroids, you can create intermediate, and if you have liver cells, for example, yellow, and in the filial cells you can create this mini block. And if you start to do it systematically layer by layer, and if they fuse, then you can create three-dimensional, vascularized, perfusible, liver-like tissue construct. Now, again, if you look on kidney, there's three main elements in kidney from anatomical point. There is branching arterial and venous tree, there is ductal system, and there is parenchyma. But if you look on vascular tree, from renal artery to capillary, it's probably 10 or 12 branching order. So when people say that we get vascularization and see capillary, or if we can create large diameter blood vessels, it doesn't automatically mean that they built whole vascular tree. And also anatomy of vascular tree is very sophisticated. It's follow the principle of optimal branching in such a way that you, with minimum efforts, minimum energy, provide maximal supply of oxygen and other necessary nutritions. So this is actually data from Brazil, from Rio. This is corrosion cast provided by Dr. Sampio on kidney. And this is my microdissections which demonstrate that vascular tree start from renal artery is very heterogeneous, but basically it's dichotomicous branching, and you can measure length, angle, and also diameter and thickness. So we've done this, and now we're writing paper for this. We're also using mathematical modeling, because you can see that if you assume that tissue spheroids volume is the same, and if there is tissue fusion process, then of course diameter is reduced. So if you want to create blood vessels like this, at first you must create mathematical model or skeletonization and branching pattern. Then you must use coefficient of retraction, which you can calculate, and then you create blueprint. And when you print construct, then the blueprint usually reduced twice. So using Surface Evolver software with Ken Brecker from Pennsylvania, we demonstrate that if you have one layer or 3 layers or 5 layers of tissue spheroids, usually after fusion, internal diameter reduced 25–30%. So basically, if you want to print kidney such size, blueprint must be twice or 3 times more. And now I am very happy to show some image which generated here, and so beautiful that I couldn't resist. So what is actually demonstrated, if we know thickness of wall, and if we know diameter of a wall, we can calculate what is how many layers of tissue spheroids we must put to create specific diameter. And we calculate that first, second, and several other branches you can create using solid tissue spheroids, and then you must switch either to smaller diameter of spheroids or use luminized tissue spheroids. And another nice slide from Brazil. So this was computer-aided design, and you already saw in presentation of Dr. Da Silva that it's already possible to print this using Dr. Ivan Malone printer. But of course our goal is to print living cells, and that's why we're working also on bioprinter. Now, our competitor from Switzerland, they actually done this without printer. They use molding. So they create vascular tissue spheroids and create this tubular mold, and you can see this single tissue spheroid, they fuse, and after fusion you have this real tube. And I talked with Jens Kelm, I say, what is mechanical property? He said after 3 or 4 weeks it's actually good enough for surgical transplantation. But there is some things which is unexpected. You see, originally there was 2 layers, now it's already 4. So tissue spheroids can move, some kind of, it's called instability or ejection. So our plan is basically start from stem cells, create differentiated cells, then create the diversity of tissue spheroid using scalable approach, and then start to build at first small mini blocks, and then finally whole tissue. Now, what is our cell source? Sorry, this is art. It's art. So, I think Americans have a huge national resource. And fast food also create a lot of stem cells. So there is a company, Cytori Therapeutics, which together with Olympus designed this machine. It's called Solution. You take your biopsy, basically liposuction fat, put in this machine, and after 2 hours you have autologous stem cells. And so there's no any immune response, and it's your cells. It's already approved, I think, in Japan and Europe. And in the United States, General Electric Healthcare already commercialized this machine. It's $100,000, one cycle $2,500, and maintenance $12,000. Okay, so it's not cheap. And General Electric Healthcare want to create some kind of complex solution for regenerative medicine. And this is the clinical cell sorter. It's the first step to build this complex solution. Now, we prove that if you take these fat tissue-derived stem cells and add TGF-beta, that eventually you can see marker of at first early stage and then late stage differentiation of smooth muscle cells. We prove this using biochemical molecular biology method. You can see nothing here, and it's positive. The longer you keep, the more positive. And interesting that with increasing expression of smooth muscle cells marker, proliferation of cells reduce. So because usually people ask, what's happened if you transplant organ and it start to grow? I say, don't worry about it. If you have differentiated cells, they will not proliferate too much. They also have functional property. These cells can contract collagen gel, and if you put them on ring, this is non-differentiated cells, nothing happened, but differentiated cells, you see, you have contraction, and another interesting phenomenon is called ejection. So this guy will be probably ejected. So what we saw in data of Switzerland and what we saw in our data is actually consistent. So aggregate can a little bit move. Now, this interesting phenomena, if you take cells on Petri dish, they start to produce collagen, soluble collagen. Then you change the media and all collagen is gone. So you can wait years until you have enough collagen. If you have confined media, three-dimensional, then all soluble collagen stay there. So that's why three-dimensional give you much more collagen elastin. But if you add also endothelial cells, that number also increase. So more natural environment, more three-dimensional, more different cell type give you much better outcome than just single cells on monolayer. Now, we prove that if we take these cells and put them in hydrogel with endothelial cells form network. But it's interesting, practically all these induced smooth muscle cells, they find endothelial cells and they attach them, and basically you can see colocalization. So they became pericytes and smooth muscle cells around this vascular network. So they basically typical vascular smooth muscle cells. Now, we calculate if diameter of tissue spheroid is, let's say, 250 micrometers. So 1 millimeter is 4 tissue spheroids. 1 centimeter is 40 tissue spheroids. If you have organ like kidney 5 centimeters, then you must have 200. Now multiply on 10 centimeters and 5 centimeters, so basically it's millions of tissue spheroids. So when I talked with my postdoc, she said, you want me to do this by hand? I will have arthritis. So we say, okay, I can buy you this machine. It's increased your productivity 8 times. She said it's not enough. So we decided to buy this machine, Emotion. So it increased productivity even more. And that's how we start to play with idea how to create scalable production of tissue spheroids. This is our first attempt, and again, thanks to STI and Dr. Da Silva, we was managed to create these small pillars, which create this recession. So if you put cells in suspension, in non-adhesive hydrogel like agarose, you can see these aggregates. So idea was that using this mold, you can create a lot of tissue spheroids, and basically all process of cell seeding and tissue spheroid can be completely robotic and automatic 24 hours, 7 days in a week. Huge productivity goal. But the problem is, number one, you see this empty space, and sometimes cells attach to this or stay there, create aggregates, so we have some problem. So I came here, Dr. Da Silva said, you know, Mother Nature has solutions for this, it's called honeycomb pattern. So that's what we're developing now, more sophisticated approach. And I was really surprised when I understand there is already 5 companies which working exactly on the same problem. In sphereo, microtissue, nano 3D, bioscience, and so on. So basically, generation spheroids is already business. If we can do it high standard size with high productivity automatically, that's actually big advantage. I show one of the slides that you can create Janus-like structure, and there is microfluidic device. You can mix 2 polymers or 2 cells. Let's say one of them contain magnetic nanoparticles, one not, and then you can polymerize if it's a photosensitive hydrogel. You can create Janus-like structure, which can be, as I said, self-directed, self-assembled. Actually pretty close to the concept of Hood-Lipson, which say that you can create digital material, but in this case it's just you throw away this material and they self-assembled like magic. Now, when David Weitz from Harvard University visited us, and I was so excited to demonstrate that we develop scalable technology, he said, it's still only 1,000, you need millions of tissue spheroids. I say, so what I can do? He said, you can use power of microfluidics. You see on this picture, you can generate 10,000 droplets per second. Imagine productivity, 10,000 droplets per second. I still couldn't comprehend this, okay? There is also some other technology, because if you just use a very, very thin tube, because of surface tension, you have huge one. But if you use some kind of vibration, which is called acoustic excitation, then you can control diameter of droplet. So what I try to say, that formation of droplet, which I also mean tissue spheroids, is an engineering problem, and you can solve this if you use, and again, to go, I think today Taka told me that he already designed microfluidic device which allowed to realize our dream to create not only solid but also luminized tissue spheroids. That's another project which is under development. So can we do it? Yes, because David Weitz from Harvard already done this, but for emulsion. If we switch from emulsion to hydrogel, and if hydrogel will have living cells, then we can generate not only solid, not only luminized, but also multiluminized structures like glomeruli and so on. Now, concerning the bioprinters, I can say there's already 5 companies: Organovo, Cyperio, Delta Robotics, and Vision Tech, and my company, which tried to create a commercial bioprinter. So bioprinter is already business. There's only one problem: the cost of this machine, sometimes $250,000 or euro. You can see our first variant of printer. We use Fishman dispenser and Roland XYZ robot. Then we create something which is more friendly for hood, or you can build hood like Cyperio, but it became $250,000. You can use very cheap variant, which I think Ivan will talk more. And this is the first variant of Envision Tech bioprinter. As I told you, now it's big business. Now, what you can do with these bioprinters, you can dispense either hydrogel with living cells. You can see there's some granularity here. You can see green light because cells are GFP labeled. Or you can dispense aggregates like this, either on dry or on hydrogel. I think if you use digital or droplet-based printing, not continuous or analog, you have more room to create more sophisticated mosaics. It's like if I want to build only from this, then I have limited. If I have from points, I can do anything. Now this is our first variant. Second variant, this is Cypheria printer. Bioreactor actually also reality. You can see here a company from Charleston which already developed this cooler. You see here, I think in testing, but usually designed for kidney. It basically allowed you to perfuse organ and then keep this in cold conditions, so it extends life of a transplant. $18,000 FDA approved. They're working on a bioreactor for lung and also for liver. So design of bioreactor is basically underway. But again, we're thinking how to design bioreactor which allowed us to buy time, because even we print blood vessels, it takes time until blood vessels became mature and will be allowed. So we designed this, and now with Rodrigo, we want to use a mathematical model to estimate what is the optimal distance, what is optimal porosity, and also there's big question, what type of material we want to use. Because as Dr. Da Silva said, it will be shish kebab, so we can put this and then we remove. So it must be very, very thin, very, very strong, and very, very porous. But porous in such a way that we don't spend too much media, so it must be irrigation dripping, like in Israel when they put this irrigation for grow plant. So there's a lot of challenges of engineering, material science, and I talked with Kostyan Novoselov, it's a Russian guy who recently got Nobel Prize for graphene. I say, you told me that graphene is probably the strongest material in the world, stronger than diamond. He said, okay, if you can find some polymer and put nanotube inside, then you create very, very thin needles which can fit to your design. So this is another project which is also working with STI. And finally, I never thought about this, okay, I thought about this, but even when I start to say people that you can print organ in vitro, people believe that you are crazy. But then people say that there is such company, Da Vinci, which, no, company Intuitive Surgery, but product Da Vinci, which create first robotic surgical tool. Basically, patient is here, surgeon is here. This is the surgeon's hand, but he doesn't work by hand. A robot imitates its movement. And you can do operation, for example, when surgeon in France and patients in New York, or patients on the Earth, no, patients in the space and surgeon on the Earth. So machine costs $2 million. The sale grow 25%. 70% of these machines never used because it's too difficult to learn. But if you are chairman of Department of Surgery in American University and you don't have Da Vinci, you are from third world. Okay, so everybody buy this machine like crazy. The beauty is that you can create machine which people buy for $2 million and buy like crazy. So I don't know, you saw this movie in 1997, Travolta and Gates, criminal and policeman, they changed the face. The problem was ear, so they designed, okay, we can use laser to print, so 100% science fiction. In 2003, Lee Weiss, who created robot who run on Mars, he said, okay, if we can create printer in vitro, why we couldn't adapt this to printing in vivo? But again, I talked with Abe Rachenthal, and he said, let's call this project, he's director of 3D System, which controls 60% of rapid prototype. He said, let's call this project Michelangelo. I say, why Michelangelo? He said, because Da Vinci. So idea is to create a printer which can be served as a surgical tool. So basically, instead of building organs at first in vitro and then transplant this, you can do it directly on the patients in the operation room. Very crazy idea. But in 2009, at least 3 groups, one in Cornell, you can see and listen later, one in Bordeaux, Fabien Vermelot, I forget his name, French name, Fabien from, and one group also in Anthony Atala, they seriously start to talk about bioprinting in situ. And actually, Atala started to print skin. So, chairman of department said that if it's true, then there's no more such things as a science fiction. Just question of time and money, and will, and belief. And so again, this is the finish. So what I realized that it's not enough to have only bioprinter. You must have whole bioassembly line, like assembly of cars. You must have cell sorter, you must have tissue biofabricator, printer, you must have blueprint before. There's a lot of things. So basically, future plant will be not so simple as I think before. But if you want to create clinical, then it can be reduced to one, but machine will be very expensive. And again, this is our printer. You see this Fishman, and company Organova in San Diego, they modified our printer. They changed Roland on standard XYZ machine. They add 2 Fishman nozzles. One Fishman nozzle dispense agarose, blue, and one dispense not tissue spheroids, but rods, because when they use tissue spheroids, until machines start to work, they already fuse. So they decide to use rods. And you can see robotically printed blood vessel. So Organova licensed our technology, and I said I don't want to have any stocks because I have conflict of interest if I continue. So I couldn't be millionaire, sorry. In any case, this is the 2 machines, what we create. This is the 2nd generation, and as Dr. Da Silva demonstrated, we have already 3rd generation. What I realized that if you're a development biologist, you will never can assemble functional bioprinter because your level of knowledge is limited. So this is 2 nozzle Nordson and Fishman. This can spray hydrogel, it can print aggregates. And I hope that during my visit, this machine will work. We develop software, create first product, and eventually our dream became a reality. So one thing which excites me today, 2 guys from Austria create printer which cost 2,000 practically, and you see the size. So desktop printer is reality. And because there's no questions, I want to say something. I already felt time in Brazil, yes? Sempre há tempo para cafezinho brasileiro.
Thank you, Professor Mironov. Nós adiantamos um pouco nossas apresentações, então nós estamos preparando um coffee break lá fora, para a gente poder conversar um pouco, quem quiser encontrar os amigos aí, discutir algumas ideias enquanto se diverte um pouco. Enquanto isso, o Eva Malone e o Turf se preparam.